So now let's look at the features of XtremIO, and we'll walk through these in a bit more detail, and you're going to see these again as we go through the rest of the course. Some things will impact how we configure it. It'll be noted, as we go through and change things, but some things you just should understand if you're planning on deploying XtremIO in your environment. First is active-active controllers. What this means is that in a storage array, you have kind of the brains of the operation, the hardware that manages the disks, that talks to the servers or the host. Those are normally called controllers or storage processors. XtremIO, we call them controllers, but really in the end, it's the same thing. Heads, controllers, storage processors, you may see people call these things different names, but it's really the same thing. What we mean by active-active is that within XtremIO, you have at least 2 controllers, and we'll talk about how you scale up in a minute, but so you could have more, but they're all active, meaning it's not active and passive. Both of the controllers are always working. They're taking I/O in and out, to and from the servers and from the host, to and from the solid-state disks on the back end. You don't have one that's holding the load, and if he fails, it shifts to the other one. Or you don't have some things, in a lot of traditional arrays with active-passive controllers, some volumes are managed by the first controller, some volumes are only managed by the second controller. If one fails, they all shift to the other one. In this case, any volume or LUN can be accessed by either controller at any time without any penalty or degradation in speed. So that's a fairly new thing. Not completely new, as there are active-active storage arrays out there, but it's an important distinction. And the nice thing is you can scale these up. As you add more controllers, you'll get more performance because they're all actively servicing requests to and from the host. Inline deduplication. Right now, flash is very expensive. It's coming down in price, but it still costs significantly more than spinning disks. You can go and buy a 1 terabyte hard drive for substantially less than you can buy a 1 terabyte solid-state disk. That's important because flash is very fast. We normally buy flash because we want the best performance. It's a term we sometimes call price per IOP. An IOP is a I/O or an input-output operation to and from a host. So a normal solid-state disk, well, let's say a good enterprise-level solid-state disk, may do 30,000 IOPS on a single disk. And it costs a lot, but you get 30,000 IOPS. So your cost per IOP is low. If you go look at a 1 terabyte 7200 RPM drive, yeah, the cost is low, but you only get maybe 130 IOPS out of that. Actually, that's a bit high, usually somewhere around 90 to 100. So it would take a lot of those to equal the performance of a good solid-state disk. And therefore, the cost per IOP is very high on the regular hard drive, but the cost per gigabyte or terabyte is low. So coming back, that's why we need things like deduplication. So deduplication says, it breaks up the data that it's storing on the disk and says, I've already got a copy of this data. I don't need to store 2 copies of the data. So think about things like virtual environments with a bunch of virtual machines, a bunch of copies of Windows 2008 Server or 2012. How many times do you need to store those same DLLs and those same files? Well, if you stored it every single time, you'd churn through that capacity very quickly, even though you weren't really getting the use out of the performance, and you'd be unhappy. With deduplication, you can then dedupe all those things down. So instead of 20 or 50 or 100 or 1,000 copies of Windows, you really only have one with just a unique data set. And that lets you get a lot better efficiency out of these storage arrays, and therefore you get more bang for your buck. The dedupe in the XtremIO is always on and it's always working. It doesn't turn off. You can't actually, at least from anything that I've seen, even turn it off if you want to. It's definitely not in the UI. So it's always there. And we'll talk about how it works in a little bit and how it's really ingrained to the system in how it stores data. You also get a scale-out architecture. You can keep adding what we call bricks, and we'll go over what a brick is in the course, but you can keep adding bricks as you need more capacity or performance. So you can start with 1 brick, then go to 2, then go to 4, and hopefully one day they'll let us do more than 4. But you don't have to go out and buy everything up front that you need, and this is known as scale out. Scale out means I'm adding another brick, which includes controllers for performance and CPU, as well as capacity. You'll sometimes see people talk about if an array scales up. Scaling up is what most traditional storage arrays do, meaning you have two storage processors and some shelves of disk. And when you want more capacity, you add another shelf of disk and another shelf of disk. You're scaling those controllers up. You're not ever adding more processing power or more controllers as you add capacity. XtremIO scales out. You add capacity and performance in the way of controllers and CPU and memory as you go. So you just keep this linear scaling model so that you're not just adding more SSDs and suddenly you have a bottleneck on your controllers. Everything scales together. We also have the concept of what is known as drive level garbage collection. And this is kind of a minor feature. It's something that if you look at different all-flash arrays, you'll see talked about. So I'm going to talk to you about it here as well as a little bit later when we talk about performance. But the bottom line is that when you write to a solid state disk, there's some things that go on within the disk that cause it to need to be kind of reorganized, let's say. So often with SSDs, it'll write in 4 kilobyte or 4 KB chunks. What if you don't need to write 4K? What if you only need to write 2K? Or you wrote 4K and you delete 2K? You end up with what are called these cells that are halfway written to. So you've got little fragments of free space all over the place. And eventually something needs to come back, kind of do this garbage collection and rewrite the data so you get full cells with full 4K of data. And then you have empty cells with blank data without anything on them. And the reason is you want to be able to write in 4K chunks onto an empty 4K cell. It's much faster to do that. If you try to write to a cell that's already got 2K on it, what the systems actually have to do, the SSDs do, is they read that 2K, clear the cell, and then write back the full 4K. So you end up with a multi-read-write operation. What I'm getting to is that a lot of systems use system-level garbage collection. So basically the system, the controllers, the process running on the array goes back and does that at some point in time. When an array isn't that full, say 30 to 60%, it's not a big deal because there's a lot of free scratch space to move stuff around. But when you get up to like 90%, the scratch space is less and it can cause performance issues. XtremIO does drive level, meaning it lets each individual drive handle garbage collection, which is supposedly a better method, meaning the system doesn't have to get involved, it doesn't take CPU from the controllers, it doesn't take a process that blocks I/O. You'll hear people go back and forth which is better, but if you get into a conversation or you're looking at this or you're wondering how it works, the XtremIO does drive level garbage collection. It lets the drives themselves do it. And it also has a really good management interface. So here's an example of that. It's known as XMS, XtremIO Management System. Not much going on here because there's 0 megabyte per second throughput and everything like that. This is from a brick that I had just set up in our lab that we're actually going to use in some of the labs later in the course. But it's very easy. It's web interface, obviously, as you can see, runs Java, but get to it through the web. And it's very simple to use, very few knobs, very little tuning, anything that you have to worry about. And it kind of goes against what we normally see in the old traditional storage arrays, which are very complex. They're very daunting, especially to somebody without much experience. With this, it's very straightforward, as you'll see in the labs.